Earlier in last class we discussed about small signal amplifiers. These amplifiers are used to amplify a weak signal, and actually what is the procedure for amplifying signals for practical use is that we have a number of stages of amplifiers connected in series. So, initially we have to amplify a weak signal whose small voltage will be amplified, and this output voltage will be again amplified by using other stages in between, and finally what will be driven by this output voltage is that practically we have to use number of devices like loudspeakers, cathode ray tubes, etc., but these require a large amount of power to drive them. So, the amplification which we have done using the small signal amplifiers, this is not enough to drive these devices because they require large amount of power. So, these small signal amplifiers which are typically used for voltage amplification, they are in the initial or intermediate stages of the whole amplification, but at the final stage we require power amplifiers. So, these power amplifiers are basically large signal amplifiers which can handle large amount of power, and this power is finally used for driving the devices like loudspeakers, etc. So, we have to know about the large signal amplification. That is the topic we are going to take up today. So, the devices like cathode ray tubes, loudspeakers, servo motors, etc., they require large power to drive them, and that is why we have to use a large signal amplifier. Now, as the large signal is the name is used, that indicates that the signal which it is handling will have a high magnitude. That means the amplifier which is the large signal amplifier, this will be using currents or voltages which are higher in magnitude, because earlier when we discussed the amplifiers which are linear, because we were using a small signal, so that the amplifier is still in the linear operation range. Now, we will be using large signal amplifiers, and that is why the transistor which is used in the amplifier, it must be power transistor. That means this transistor is a special type of transistor which can handle large amount of power in watts. So, the power transistor has to be used to handle such high power which is used in the large signal amplifier or power amplifier. So, if we now discuss or see an audio amplifier having the different stages, then we see that the final device which we will be using is a speaker, that is loudspeaker, but initially we give the audio signal to a microphone. So, microphone will be converting an audio signal to an electrical signal, and that electrical signal will be first amplified. That means the voltage of this signal will be amplified by this voltage amplifier. So, this is a small signal amplifier because the microphone produces the voltage of order of millivolt only. So, that has to be first of all amplified to have a higher magnitude of the voltage. Now, one voltage amplifier may not be sufficient. So, we will be using a number of voltage amplifiers in series. That is why here, for example, it is shown 2 voltage amplifiers in cascade. After voltage being amplified, the final stage is having a power amplifier. So, this amplifier will be used finally, whose output will be given to the speaker or the loudspeaker, because loudspeaker requires a high power to drive it. So, at the last stage, the amplifier which is being used is a power amplifier or a large scale amplifier. So, that amplifier has a higher amount of voltage and current, because the multiplication of voltage and current gives you the power. So, we have in that amplifier a power transistor. If we typically consider a transistor amplifier, that will be using a power transistor which can handle a large amount of power or dissipate a large amount of power. So, now the power amplifier which is used is of different types depending upon the time for which the amplifier operates, means the time of conduction of current. The amplifiers can be divided into 4 types. These are class A, class B, class AB and class C amplifiers. So, the conduction angle, that is the time or the angle for which the collector current will be flowing, that differentiates between the different stages of the different types of the power amplifiers. For example, in class A amplifier, the conduction angle is 360 degree. That means, if we look into the collector current, then for the whole 360 degree angle, the current will be flowing. So, at no point there will be any portion where the current is 0. So, we can see that the whole cycle will be there from 0 to 2 pi or 0 to 360 degree, and this is a typical linear amplifier which earlier we discussed when discussing with the small signal amplifier, because if we recall, then we were studying when discussing about the small signal amplifiers in the linear operation range. If we bias the transistor properly, then we get the output collector current flowing throughout the cycle from 0 to 360 degree, and at no point of time there was any cutoff or a saturation occurring. So, that idea is still applicable in the class A amplifier. Here it is linearly operating. That is why we can see that the collector current is flowing for the whole cycle from 0 to 360 degree, and that is because the DC collector current or the quiescent collector current is positioned in a very proper way, so that during the operation at no time the collector current either goes to saturation or cutoff. And here we can see that the DC collector current, which is the Q point, is positioned well enough at properly positioned, so that during positive and the negative half cycle the collector current rises and falls, but it does not enter into the cutoff or the saturation. So, this is a typical linear operation of amplifier, and this is the class A type of amplifier. Now, apart from this class A type of amplifier, there are other types of power amplifiers also, which are used because in the class A type of amplifier, what happens is that there is a huge power loss because of the DC collector current being flowing throughout the cycle, and that we will be discussing later how the power loss can be minimized by using other type of amplifiers than class A amplifier. So, in class B amplifier, what happens is that during the negative portion of the cycle, collector current is not flowing. So, here we can see that only in 1/2 cycle from 0 to 180 degree the collector current flows. So, this is class B amplifier, and here the conduction angle is exactly 180 degree. So, from 0 to pi the conduction takes place, and from pi to 2 pi the conduction does not take place. So, this is a typical example of an amplifier where you are locating basically the quiescent current at the cutoff. That is, if we are placing the quiescent current here, then in the negative half cycle we are entering the cutoff region. So, there cannot be any current flow. Another type of amplifier is class AB type of amplifier. So, in class AB type of amplifier, the conduction takes place which is greater than 180 degree, but less than 360 degree. So, here you can see that in class AB amplifier, the collector current is flowing beyond this pi, or the conduction angle even greater than 180 degree, there is current, but not throughout from pi to 2 pi. That means, it crosses this pi, beyond pi also there is conduction, but then it stops conducting, and that is why the conduction angle is between pi and 2 pi. It is greater than pi, but less than 2 pi. So, here we can see that the DC current, DC collector current or the quiescent current capital I capital C is placed here at this position, and that is why during the positive half cycle we can see that the collector current is flowing. Again it also flows when the angle is greater than pi, but at this point the collector current enters into cutoff. So, from this point to up to this point, this portion the collector current is 0. Again it will be flowing and rising. So, this will be continuing. So, because of the position of the DC quiescent point or the DC collector current, the conduction is taking place in this fashion, and that is why we get conduction up to an angle which is greater than 180 degree, but it is less than 360 degree. That means, this AB type of power amplifier is in between A and B. It is not A because the conduction angle is not from 0 to 360 degree whole, neither it is B because in B type of power amplifier the conduction angle is 180 degree, but it is in between. Another type of amplifier is there which is known as class C type of power amplifier. So, in this class C type of power amplifier, the conduction angle is even less than 180 degree, that means it is even less than the class B type. So, here we can see that the collector current which is flowing, it is not even 180 degree or pi. It is for even a lesser portion it is flowing, and that means it is basically not flowing even for 1/2 cycle of the whole cycle, that is it is only less than 1/2 cycle the collector current is flowing. So, it is even worse than your class B type of amplifier. So, broadly we are having these 4 types of power amplifiers: class A, class B, class AB and class C, depending upon the conduction angle, that is for the time for which the collector current is flowing, that means whether it is flowing for the whole cycle from 0 to 360 degree, or it is flowing for only 1/2 cycle, or it is flowing for a conduction angle between pi and 2 pi or even less than pi, we classify the power amplifier. So, we will be now discussing the amplifiers which are classified in these 4 ways one by one. So, let us take for example class A type of power amplifier first. Now, we will be discussing the class A type of power amplifier first. The class A type of power amplifier can be classified into 2 broad classes. One is the series fed class A power amplifier and the other is the transformer couple class A power amplifier. Depending upon what device is used in the amplifier, these 2 classes are made. For example, in series fed class A power amplifier, we will be observing that we use a transistor amplifier, that what was used in small signal amplifiers using BJTs. Similar type of circuits will be used for class A power amplifier, where transistors are used, and in transformer couple we will find that a transformer is used for coupling the device to the amplifier. That means, at the output stage we will be feeding the output power through a transformer to the device which we are going to use. So, in series fed class A power amplifier, the transistor which will be used will be a power transistor which can handle large amount of power, and there are facilities for handling large amount of power in such type of transistors. And the circuit which is used, we can see that this is a familiar fixed bias circuit where biasing is done through a resistance RB, and this type of fixed bias circuit we earlier we got. So, this is an example of a fixed bias circuit. There can be potential divider biasing scheme also, but we are taking here for example a simple series fed class A power amplifier where a fixed bias is used and a power transistor is used for amplification. The signal which is to be amplified is Vs, and there is this capacitance C1 to couple the voltage Vs, and the reason for the capacitance C1 being used we all know. It is a capacitor to block the DC component, because capacitor is like an open circuit to DC, and the output is V naught, say, that is going to be used finally. So, if we now consider this circuit and try to analyze the efficiency of this power amplifier. By efficiency we mean that ratio between the output power to input power. Now, this power amplifier is drawing power from where? It is using a VCC, that is a DC voltage it is used, and the power being drawn is the DC power which is supplied through this VCC, and the power which is drawn is VCC into IC, where VCC is the DC supply and IC is the DC collector current. So, this much amount of power is used or it is being supplied, and to get the idea about how much efficient is this power amplifier, that means how much output it is producing, that we must know. Then we can get the efficiency of the power amplifier by finding the ratio between the output AC power which it is developing to the input DC power. So, in this circuit, if we look into the characteristic curves and the load line, which we already know how to draw the load line, is the extreme conditions of the voltage VCE and the current IC. Those 2 points have to be connected on the characteristic, that is the output characteristic of the transistor. So, we get a load line which is defined by these 2 extreme points, and this load line, if we draw on the characteristic curves, that is the output characteristic, that is the characteristic between the output voltage and output current VCE and IC, then we know the intersecting point of the load line with the characteristic curves, where the characteristic is that one which is giving you the DC base current. So, we recall that the Q point can be determined by finding out the point where the load line is intersecting the output characteristic curve for that particular value of the DC base current. So, in this plot we are having the output characteristics of this transistor amplifier, and it is a general characteristic. We are not defining exact values because it depends on what VCC you are using, what is the resistance you are using, RC, and even without defining all those values, we are just plotting the general characteristic curve, and here these are the 2 points VCC and VCC by RC, these are the 2 extreme points. So, joining this we get this DC load line which has a slope of 1 by RC, but it is a negative slope. So, minus 1 by RC is the slope of this DC load line, and the point where it is intersecting the particular characteristic curve for the value of IB, because this IB is the DC base current flowing in this circuit. So, this gives the Q point, and this Q point is giving the DC values of the collector to emitter voltage VCE and collector current IC. So, this is the load line for this particular transistor amplifier which is in class A type of operation. So, here one thing to note is that the quiescent point Q is positioned almost at the middle of the load line, and that is required condition for class A operation. If Q is not located at the middle of the around the middle of the load line, suppose it is shifted either to the saturation side or to the cutoff side, then we will not be getting a class A type of operation, because in power amplifiers the base current will be high. It is not in the order of microampere range as we earlier got for the small signal amplifiers. It may be in the order of milliampere range. So, the swing of this base current will be high, and that is why corresponding values of the collector current will also be high. So, in order to get a symmetrical swing of the collector current, we must position the Q point around the middle of the load line. That is the foremost condition for the class A operation or linear operation. Now, the largest possible or permissible value of the collector current, that is the peak value of the collector current, if we see in the load line again, the collector current can swing from the DC collector current to a value given by the value of the maximum, and that can be found out because if we consider this maximum value of this VCE, that is VCC. So, the Q point is located here. So, in the collector current we will be getting, basically we will be getting from the DC value a swing like this. This is the DC collector current, this is the peak value of the IC peak, and this will be the maximum allowable peak of the collector current, and that will be how much value? That is because this is half of VCC, this point is VCC by 2, this is VCC by 2, this whole is VCC. So, this is VCC by 2, this is VCC by 2, and so this the maximum can go on the either side from the DC value is VCC by 2 RC, that is we get this swing and that should be VCC by 2 RC, and similarly towards the lower side also VCC by 2 RC, because this is the total value is VCC by RC. So, the allowable peak of the collector current in class A operation will be VCC by 2 RC, and the largest permissible collector to emitter voltage peak is VCC by 2, and that is very evident here. The largest swing it can be having, the VCC can have, it will be like this. So, this value if we want to find out, this will be VCC by 2, and we know that the input DC power is VCC into IC, that is the DC collector current, and this is denoted by VCC into ICQ. Now, the power which will be delivered to the load, that means the output power. Now, we have to find out the output power which is AC. So, in order to find out the output power, we have to find out the power which is the multiplication or the product of the current and voltage, and the current is the collector current IC, but that value is RMS value, root mean square value we will be taking, because we are finding out the output power, that is AC. So, the value that we should consider is the root mean square value, and that value is nothing but the peak value by root 2. So, IC RMS into VCE RMS, this product will give you the output power, the output AC power, and that is we are finding out by finding the RMS value by IC peak by root 2, and the VCE RMS value can be obtained by VCE peak by root 2, and we know what is the IC peak, that is the whole swing divided by 2. The whole swing is the IC has this is the IC capital, and it will be having this type of waveform. This is IC peak and this is IC negative peak. So, the whole is the IC, this value if we consider, this is IC peak to peak. IC peak to peak is the whole swing of the collector current, and that whole swing peak to peak divided by 2 will give you the one peak of the collector current, and that we are using here IC peak to peak by 2, that is the one peak value divided by root 2, and similarly VCE peak to peak by 2 divided by root 2, that is the RMS value of the VCE, and that gives us IC peak to peak into VCE peak to peak by 8. So, now in order to find out the efficiency of the power amplifier in class A operation, we find out the ratio between the output power and the DC input, because we are feeding an DC input, and how much power at the output we are getting, that ratio between the output to input will be giving you the efficiency. Now, if we plot this, if we find out this P naught AC by P naught DC, P in DC, P input DC into 100%, by substituting these values, we can find out the efficiency, that we will find out. But one thing we must also consider here, one important aspect is that how much power is dissipated by the transistor, because we are feeding an input power which is VCC into ICQ, that is the DC values, and out of this input power we are getting an portion at the output as AC, that is the output power in AC, which is the IC RMS into VCE RMS, and now some portion of the input power is also wasted. The portions which are wasted, one due to the collector resistance RC, there will be a power wastage, because IC square into RC, IC square means square of the DC collector current, because the DC collector current is always flowing, and that will be causing a power loss, that is because a power is absorbed by the resistance in the collector. So, IC square RC will be that power absorbed by this resistance RC, and the power which is dissipated by the transistor as heat, if we want to find out, we can find it out. PD is the power dissipation as heat, which is dissipated or wasted by the transistor as a heat, because handling of large amount of power means it will be causing considerable heat, that is the wastage of power, and that can be found out by subtracting the output power and the power absorbed by this RC from the input. So, that is P input DC minus IC square RC minus P output AC, that will give you the power dissipated by the transistor as heat. So, now if we consider the maximum collector to emitter voltage swing, peak to peak maximum swing can be VCC, because that is obvious here in this plot. We see that as it is, as the DC point or the quiescent point is located at the middle. So, the maximum swing can be only up to VCC, that means 0 to VCC can be the swing of the VCE. It can swing from DC value to this point, and then it can come in the negative half cycle up to this point. So, the total peak to peak swing, this peak to peak swing, if we consider, that is VCC, and peak to peak swing of the collector current, that if we consider, that will be VCC by RC. So now if we consider the maximum output power, considering these maximum cases of the peak to peak swings, then P naught AC maximum can be IC peak to peak into VC peak to peak by 8, because we have seen already that the output power is IC peak to peak into VC peak to peak by 8, and what is this IC peak to peak? It is VCC by RC, and VCE peak to peak is VCC divided by 8. So, we get VCC square by 8 RC is the power output, that is the maximum power output possible. So, now what will be the efficiency of this amplifier that can be found out by dividing this output power by input power. Now, what is input power? Pi, it is a DC power, that is VCC into IC, and what is the IC at the collector point? Quiescent point. This quiescent point has IC, which is equal to VCC by 2 RC. So, putting it here, VCC by 2 RC is the collector current, DC collector current, that means the current at the quiescent point. So, we get the input power P input DC, this is a DC power, mind it, we are feeding it by means of this battery or the source, which is a DC source, which is VCC. So, P input DC is VCC into IC, substituting IC by VCC by 2 RC, we get the expression as VCC square by 2 RC. So, now we know what is the output power, now we know what is the input power. So, we can find out the efficiency. So, maximum efficiency of this power amplifier is given by VCC square by 8 RC by VCC square by 2 RC, just substituting the values for output power and input power, multiplying by 100%, because efficiency is always given as percentage value. We get finally 1 by 4, because these cancel, only remaining is 1 by 8 and this 2 will be going up. So, 1 by 4 means in 100% it will be 25%. So, from this value of efficiency, what we can infer, conclude is that efficiency of this class A power amplifier is very low, it is only 25%. That means you are feeding a power, DC power, and only 25% of this DC power we are getting as the output. So, much wastage is now occurring in the amplifier. One wastage is very obvious, that is the heat is generated, but that is not very easy to avoid. But what is another point to be noted in this type of a class A amplifier is that IC square RC, this loss, this power loss, this is also a wastage of power, because of the flowing of the DC current always or throughout the operation, a constant DC current IC is always flowing in this transistor for the whole cycle. So, IC square RC, that is I square R loss, that is the loss occurring in the resistance which is connected in the collector of this transistor amplifier. Here this RC is causing a power wastage, and we have to devise some means to reduce or decrease that power loss which is occurring in the RC. So, in order to increase the efficiency of the amplifier, class A type of amplifier, what is done is that transformer couple amplifier is used because of much wastage of power being occurring in this RC which is connected in the collector. What is done is that a transformer is used to couple the output device to the amplifier. Instead of RC, what we will be having is an inductive coil, and that will be in the primary side, and the secondary side will be having the load or the device which is connected. So, instead of this RC, next we will be having a transformer winding in this, and that will be reducing the loss occurring by this resistance. So, that we will be discussing next. But now, before going to transformer couple amplifier, now let us try one example dealing with this class A series fed type of power amplifier. So, in this example, we are having this class A series fed power amplifier, and the value of the beta or the transistor gain is 25, RB is equal to 1 k ohm, RC is equal to 20 ohm, VCC the supply voltage is 20 volt. Now, we are to calculate the input power, output power and efficiency of the amplifier. When the base current is 10 milliampere peak, because of the supply Vi, a base current AC current will be flowing, and that has a peak value of 10 milliampere. This peak is 10 milliampere. This is the small IB, and also calculate the power dissipated by the transistor. So, in order to solve this, let us do the analysis. Draw this circuit again. This is a fixed bias circuit. It is a simple circuit using only a fixed resistance RB in the base, and that value is 1 kilo ohm. VCC is given as 20 volt, RC is 20 ohm, and emitter is directly connected to ground, and we have a DC blocking capacitor, and the input is say Vi, is a signal Vi is used. Now, beta value of this transistor is 25. So, in this circuit now, in order to find out the quiescent point, first we have to find out the Q point first, because we have to know the DC power input. In order to know the Q point, we will be considering only the DC circuit, because this capacitor will be open circuiting in DC. So, we will be having under DC condition, we will be having only these values RB, RC, this is the transistor, this portion will be open. So, there will not be any use for this, we are just ignoring this portion, and this is the circuit. So, here VCC is equal to 20 volt, the current which will be flowing, RC is equal to 20 ohm, RB is 1 k. The current which will be flowing is capital I capital C in the DC condition we are considering, and this current is capital I capital B, base current DC. So, in order to know this DC base current, what we have to do is that we consider the circuit and apply Kirchhoff's voltage law. So, applying KVL to the base circuit, what we get is that if you apply KVL, VCC minus IB into RB minus VBE, this drop we have to remember, this is the base point, this is the emitter, this is the collector. This VBE as usual we will be taking 0.7 volt, even though it is not specified, we will be considering 0.7 volt drop for this transistor from B to E. So, putting these values, because this is nothing but 20 minus IBRB minus VBE is equal to 0, this is the KVL, Kirchhoff's voltage law applied to the base circuit. So, what will be base current? So, base current is equal to VCC minus VBE divided by RB. Substituting the values, VCC is equal to 20 and the value of VB is 0.7, RB for this circuit is 1K, and we are keeping kilo ohms, so the result will be in milliamperes. So, that unit you have to remember. So, that means that is 20 minus 0.7 is 19.3. So, 19.3 milliampere, this is the DC base current flowing in this circuit. So, if IB is equal to 19.3 milliampere flowing, what is the DC collector current ICQ? That can be found out, because we know the value of beta, beta times of base current is the collector current. Beta value 25, 25 into 19.3, this many milliamperes will be flowing as the DC collector current. So, if we do this multiplication, we get a value of 482.5 milliampere. That means it is 0.4825 ampere. So, almost 0.5 ampere current, collector current is flowing, DC collector current. So, we can see, we can observe the order of the current flowing. In the base also it is 19.3 milliamperes, it is not in microampere as earlier we were getting, it is a, that is the large signal, why it is called a large signal, it is a large current in the order of milliampere even flowing in the base and in the collector in the order of ampere. And you will be finding that the voltages, collector to emitter voltage which is obtained is order in the order of volts. That is why volt into ampere, that gives watts. So, it is the power is in the order of watts, it is handling such a large amount of power. So, now to complete this, what will be now the DC value of this collector to emitter voltage? That means we need to find out the DC point, quiescent point. So, what is the VCEQ? That this is VCE. So, that is VCC minus ICRC will give you the VCE. So, VCEQ is equal to VCC minus ICRC. So, VCC is 20 volt, IC we have found to be 482.5 milliampere and RC value is 20 ohm, 20 ohm. So, we keep it in order of ampere, ampere into ohm will be giving you volt. So, multiplied by 10 to the power minus 3. So, this many ampere and 20 ohm is the resistance RC. So, this value, the calculation of this will be giving the value of VCEQ to be 10.35 volt. So, now you see that this is a very high value of voltage and the high value of current which is flowing, IC current flowing is DC value of IC flowing is 0.4825 ampere. So, the DC power we know now, what will be the DC power input, voltage into current, that will be giving you the input power. So, that we can immediately find out what is the PI DC, it is VCC IC. Okay. So, now VCC 20 volt, IC is 0.4825 ampere. So, this will be giving you in watts and that value is 9.65. If we multiplied it, we get this value 9.65 watt is the input power you are feeding into this amplifier. Now, what about the output? In order to know the output power, P naught AC output. So, that we know that it is the RMS value. We are finding out, since we are handling AC, we must consider RMS value. So, that is the RMS value of the collector current is IC peak by root 2 and RMS value of the collector to emitter voltage VCE, and VCE is nothing but, if we look into this circuit, this this is the VCE. So, VCE is small IC into RC, that is the collector to emitter voltage, because we are considering only that AC. So, if we apply Kirchhoff's voltage law, VCC minus ICRC minus VCE equal to 0, but this VCC is a DC value. So, we will be considering only the AC voltage. So, it is nothing but IC into RC, and we will have to divide by root 2, because IC peak into RC will give you the peak value of the collector to emitter voltage. We are basically using P naught AC equal to the IC peak by root 2 VCE peak by root 2, and VCE peak is nothing but IC peak into RC. So, we are using here, that is what we are using here. So, therefore, we need to know what is IC peak. So, what is IC peak? We know what is the value of the base current peak, that is given as 10 milliampere multiplied by beta, that will give you the IC peak. So, 25 into 10, 250 milliampere is the value of the peak value of the IC current. So, now if we know this, we can put it here. So, this is nothing but it is 2 in the denominator, IC peak square in the numerator multiplied by RC. So, this will be giving you the value of the output power. So, now if we now replace IC peak by 250, so we get 250, but this is milliampere. So, we will be converting to ampere by multiplying by 10 to the power minus 3, and RC value we know it is 20 ohm. Now, our units are in conformity, we will be getting the output in watts. So, we get finally the P naught AC output power, that is the AC output power. So, that is given by the finally we will be getting the values as 250 square into 10 to the power minus 6, because here you just look out 250 square into 10 to the power minus 6 into 20 divided by 2. So, just do this calculation, you should get a value of 0.625 watts. Now, you see that we are getting an output power which is only 0.625 watts, but we were feeding an input which is the DC power 9.65 watt. So, that this much of wastage is happening in the amplifier. If we find out the efficiency of this amplifier which is in class A operation, that is P naught AC by Pi DC, putting the value of output power 0.625, input power is 9.65 and find it in percentage. So, it will be 6.47% only. This is only the efficiency. It is very, very less. Much of the wastage is happening in the transistor. So, what is the power dissipated by the transistor? If we find out power dissipated by the transistor, by subtracting the output power from the input power, we get the total power loss, and from that power loss if we subtract the power absorbed by the RC value, that is IC square RC, then we get the power dissipated by the transistor as heat. So, power dissipated by the transistor equal to input, which is DC power, minus output power AC power, minus the power which is dissipated in the RC, and that is ICQ square RC. Because if we look into this transistor circuit again, here the DC power is loss as IC square into RC. So, that is a loss which is actually causing the efficiency to be so low. So, now DC input is 9.65, AC power what we will be getting finally is 0.625 watts only, and this is, if we find this, 0.4825 square into 20, this value will come to 4.37 watts. You just check this value. That means power dissipated by the transistor as heat is 4.37 watts, and it is not a small value. It is quite high power is dissipated by the transistor, and that is why in order to handle such high power wastage or the high heat generated, these type of power transistors have a particular sink which is there in transistors. The sinks are used for the handling such high heat being generated by this power dissipation. So, in this class A series fed power amplifier, what we have seen is that no doubt we are getting class A operation, that is the quiescent point is almost at a middle of the load line, because in this case if we see the quiescent point VCC is equal to, we have found a quiescent point here. In this particular example, we have got a quiescent point given by 10 to the power 10.35 volt and 0.4825 ampere, and we are using VCC to be 20 volt and VCC by RC is equal to 20 by RC is 20, that is 1 ampere. So, if we consider this Q point, this is 1 ampere, this is 20 volt, and the Q point is placed at 10.35, almost 10 volt, and 0.5, almost 10 volt and almost 0.5 ampere, this is Q roughly. What does it mean actually? That we are getting the Q point around the middle of the load line. In this particular example, we have now verified that the Q point is located at the middle of the load line. That means we are getting a symmetrical swing of the, these two halves are equal. This drawing should be proper. It is, this two halves of this swing is equal basically. This type of signal we are getting, no doubt we are getting a very fine symmetrical swing of the collector current as well as the VCE. But where we are suffering using this type of class A power amplifier is that a huge amount of power is lost. Our efficiency of the power amplifier is very low. In this case, we are getting an efficiency of only 6%. So, a tremendous amount of power is lost, which we are feeding, we are getting only a very small portion, and that is not good. So, although the operation is linear, although we are getting very symmetrical swing of the collector as well as the collector to emitter voltage, but the disadvantage of this type of power amplifier which is operating in class A operation is the low efficiency. Maximum efficiency can be only 25%, that we have seen. So, we have to go for other types of class A amplifier, and that type of class A amplifier will not be using the resistance RC in the collector. Instead, it will be using a transformer coupled power amplifier where the RC will be replaced by a winding of the transformer. So, in this class today we have seen that the power amplification which is done by power amplifiers can have various operation characteristics like class A, class B, class AB and class C, depending upon the position of the Q point or the quiescent point. We get these different operations, and one type of class A amplifier we have discussed today, but that is series fed class A amplifier, but that was giving very low efficiency and large amount of power was wasted in this type of power amplifier. So, in the next classes we will be discussing the better types of class A power amplifiers, and also we will be discussing about the other types. Class A we are discussing, but we will be also discussing about the class B and the other types, and how we can increase the efficiency of the class A amplifier, that we will be taking up in the next classes.